The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Good morning. My name is Tarek Alkhrdaji, and I'm with Structural Technologies. And we're a firm that specializes in developing systems and solutions for repair and strengthening of concrete structures, mainly concrete structures. And I think by now you all understand and know that 562 is the greatest code ever created, right? From all these presentations. And you all memorize all the 5.52, 5.53. That should not be a problem anymore. So I'm going to try to minimize your pain, but I'm going to still give you some section from that document. Part of my presentation today is to talk about strengthening limits for repair and strengthening, and mainly focusing on external reinforcing systems. There are many reasons we do repair and strengthening of structures. You've seen some very good examples of that. Some of you, I'm sure, have been involved in some of these. Some of these reasons that could be design or construction errors. I'm a structural engineer, so I would like to consider all problems are construction errors. But I also work with construction a lot, so I understand and I know that there's lots of design errors as well. This specifically is a design error in which the detailing of the post-tensioning, for example, was not done correctly. And you can see that when you tension the post-tensioning, there's an outburst of the PT. So the profiling of the PT was not adequate. There are other reasons why we do repair strengthening. Deterioration. Concrete and steel are great materials that work together very well when we maintain them, when we take care of them, when we make sure that are protected. And we make sure that we use the right material in construction. If you put chloride or seawater in the concrete when you mix it, it's very bad. You have chloride in there for a long time, that's going to deteriorate the structure. There are other reasons why we do repair and strengthening, such as change of use. If I have a building sometime, and we have some of us been involved in adaptive reuse, that's a terminology now. You see parking garages being changed to, for example, office buildings changed to hospitals or to hotels. All these require change in loading on the structure. Distribution of the loads. So there are some reasons sometimes not related to duration or problem of the structure or the design, but rather the use of the structure. So from all these cases that we deal with, whether it's deterioration or it's change in use, sometimes we find that we don't have adequate capacity of the member. And we've seen some examples. And I need some additional reinforcement, tension reinforcement. And Gene did a great job in showing us an external post-tensioning system that can be used to add type of that reinforcement. But that reinforcement typically is going to be exposed. That means it's more prone to damage for different reasons. Fire is one of them. Some other could be because somebody's doing repair and damage some of this reinforcement. So this is a really major concern that needs to be addressed. And 562 tried to focus on that and bring in limits for adding capacity of the external system to make sure that the system and the structure is safe and it's not overstressed. So some of these external systems are very common. We've seen it a lot. It's steel plate. I don't have sufficient internal steel. I try to add external steel to add more capacity to the structure. And I need to make sure it's working with the structure. So what I do, I bond it. I use epoxy. I use mechanical anchors or a combination thereof. So this is a very common technique. We've seen it a lot used in buildings, bridges. Here, two cases are coincidentally for bridges. And external post-tensioning that Gene was talking about. And the concept is that I don't have enough sometimes capacity, or sometimes it's a serviceability issue. I have too much deflection or service stresses. I can use post-tensioning cables to create uplift on the structure. Like in this example, I have a cable, I put it at the high point at support, midpoint at span, and when I stress it, I create an uplift. That uplift basically creating a reverse bending that will take some of that capacity or add capacity if I want to add load to it. Different configuration, engineers can use their imagination in developing these solutions. Many ways can be done. The last external system that also becoming very, very common, it's becoming almost a mainstream technology, is externally bonded fiber reinforced polymer. I remember 15, 20 years ago when we started this technology dealing with FRP, going and dealing with building officials and engineers talking about it, and they would not buy into it. It says, what? Wallpaper. I mean, you tell me that this wallpaper is going to add strength to the structure? I can't believe that. Now it's everywhere. I see it on a daily basis on projects specified, externally bonded FRP reinforcement. These can be used to increase bending capacity, can be used to wrap column and increase their axial load due to confinement or shear capacity. We can always also use them on beam. So they're very flexible, and that's why we like them in the repair industry, because they give us really the ability to accommodate existing condition and different geometries of structural components. So these are great systems, but we need to make sure that they are protected, that if anything happened, we're not going to have collapse. So I'm going to start by talking about strength increase limit that was in the old 562, which is the current actually, 562.13. This is part of what Gene was talking about. What is that strengthening limit? I'm going to dig deeper into this part. So chapter 5.5, which is the limit for external system, it says that if you want to use external system, you need to make sure that your structure, as is right now, can take 1.2 of the dead load, 50% of the live load, and 20% of snow if I'm dealing with roof elements. And introduce a factor, AK, which is the effect of external load. For example, in fire, I have a thrust that Gene talked about. Elements try to expand that great thrust. But that thrust in fire can help me, so actually I can ignore it. So this limit, basically what it tells me that if I lose the FRP system or the external plate system, I need to be able to support this with the existing structure and considering the new loads. And the reason for that, because we wanted to make sure that if the force wing system is damaged for any reason, you're not going to collapse. So why 0.5 live in this case, while we use a live load of full service load? Because live load is never the full live load on the structure, statistically. The 1.6 we use from ASCE, for example, load factor, depending on where you come from, is a function of the maximum load expected through the history of the structure. The 0.5 actually is the mean for any specific year. That is typically what you see for any year for a structure. So that was the limit, and it was published. And we're working on the new documents. We got, within the committee, lots of discussion about this issue. And there's also discussion from the public comment on this limit. And the reason for that is, well, okay, but how can I mix everything? I mean, I know steel plates. I've been using an external system that are mechanically anchored, been working for many, many years, and sometimes increase 100% of the capacity. How can I compare these to other systems, such as FRP, for example, that are epoxy bonded? And also, the limit during an ambient temperature typical operation is different than during a fire. Because in regular operation, I don't have the effect of the fire that can damage a structure, and my fee factor could be different. Shouldn't that be separated? So as a result, different changes were done with the new proposed document, which has already been completed, and actually we just approved it, all these changes. So I had to do all these slides last night until midnight working on it. It's all fresh from the oven. The idea is we need to write really these strengthening limits rather than one limit to break it and to distinguish between several things. One of them is mechanically attached system behave different than just adhesive bonded system. And because they have more reliability, it cannot be damaged easily. That's one. Second, we need to distinguish between design strain limit for fire versus a typical everyday operation. What if this thing damaged by construction versus damage during a fire? It's completely different behavior of material. I'll explain that to you. How does that work? And then also, to provide a little bit of guidance, okay, when we say damage during fire, how do we do that? I mean, how many of you know how to understand fire rating besides each spray material? There's a science behind it. We structural engineers don't often use it. So the idea is to give guidance for the structural engineer and design engineer how to deal with fire rating. And finally, extreme events such as blast, they are not really part of everyday design that we deal with. So there is no need to include it within this limit. It can be looked at it separately. If you're designing for blast, you can go to ASCE 7. There's a chapter in there telling you about the loads. So it's not something that we thought we need to include in this code right now. So now this is what new chapter 5 look like. You don't have to read it. I'll explain some of these things. Basically, it starts by saying, well, this section is going to apply to external reinforcing system. Bonded and not bonded, but we'll distinguish between them. And it's mainly to address fire, which is the main issue, vandalism, which is if somebody come in, start cutting the carbon fiber, for example, or cut the steel plate or the PT cables, or collision. What if I have something like a posttensioning cable that is low that can be damaged? I need to account for that in my design. And it was divided into two sections, basically 552 and 553. So 552 will deal with behavior and of structure and strengthening limit in typical operations, let's call it ambient temperature. And 553, that's the separation. 553 will deal with the fire behavior of the structure. So let's look first at typical operation. A day like this, we have FRP. So what's the concern? Concern is I have material strengthening systems such as FRP that's attached to the underside of the slab. Building stays in operation 5-10 years, and suddenly we want to do renovation on it. And a contractor come in with a grinder and say, what is that heavy paint? Start cutting through and grinding off. If I design that FRP, for example, to increase the capacity significantly, there's a chance when it's get damaged, what's going to happen? Immediately I have collapse. So because it's external, because it's more prone to damage, I need to put limit on that. But then we excluded from this what? Mechanically attached, because steel plate attached with bolt, it's very easily understood that it's a strengthening system problem. It's not going to get damaged easily. Same thing with external post-tensioning. So this limit right now mainly applies to adhesive bonded system, non-mechanical system, which include most of the things that we do is FRP materials, fiber reinforced polymer materials, or if I'm using steel plates bonded with epoxy only without anchors. So what does this limit say? It says that the existing structure should be able to support a certain portion of the dead load and a certain portion of the live load with or without snow. So there are two different combinations. And the idea is I need to get my structure element. Let's say I want to strengthen this slab for flexure. I will calculate its capacity. I will use the new loads. Let's say I'm trying to add loads on the roof, like new mechanical equipment, and calculate the capacity versus the demand for this limit. If I can satisfy it, then that means I can use the strengthening system adhesive bonded. Because if it fails, I have a good capacity. If I cannot satisfy this limit, what it means that I cannot use adhesive bonded. I need to use mechanical bonded or go to some other technique, maybe add a support, add a steel beam, right, rather than attaching reinforcement. So this limits guard against sudden failure in case of damage of the external system. And of course, because it's ambient temperature, I use a standard phi factor from ACI 562 or ACI 318. And I use the capacity calculated using standard equation that we have. So everything here is a standard process that we use, except that it's a limit to guard against sudden failure of the system. And we understand why. Because again, these systems, look at it, this is beam strengthened with FRP. It's looked like a coat of paint on it. It may not be easily understood that it's a strengthening system. So it's basically to be on the safe side. Same thing here with the steel plate. This steel plate, you can see some anchors, but the anchors, you can tell from the number of the anchors, are not intended to transfer the force or the capacity of the plate. It's more like to hold it down while the epoxy is curing. So these are both epoxy bonded systems, and this limit may apply to them. So that is for the ambient temperature. What happened then during fire? During fire, this is considered more like an extreme event. So it's treated similar to the equation that's currently in ASCE 7 for extreme events, in which it says that you have to calculate the capacity based on the actual properties during the extreme event. We'll get to that. And you have to use load combination include 0.9 dead or 1.2 dead, 0.5 live, and 0.2 snow load. Now, why 0.9 and 1.2? Because sometimes the dead load may work against the live load, may help you. So in this case, you use 0.9. If they're working in the same direction, they both overstress the element, then you can use standard 1.2. Now, if this is for a fire, and if I have a fire, then the capacity of the element is not going to be the same. Why? Because the fire will degrade the concrete, will heat the steel, and its capacity will drop. So the code tells me that in here, when you calculate the capacity, you have to base it on the reduced capacity of the material. You have to determine what would be the capacity of the material during a fire event to verify that. And the code allows us to use a phi factor equal to 1. Why? Because it's an extreme event. It's something that's rarely going to happen, may not happen in the life of the structure. All we care about is just keeping it there, safe and sound without collapse. So a phi factor is relaxed a little bit. And this is common if you look in any different code. Your code, if some of you have used your code, other codes is the same thing. But a similar approach exists on all these codes. So now then the question is, as a designer, as an engineer, as someone who's working with this, or a contractor, I need to get someone to work on this. How to address the capacity of the fire? Well, there are many ways that we can do that. One thing I need to make sure that is clear, that this requirement for fire applies to all strengthening systems, mechanical and non-mechanical. So while the first one deals with only adhesive bonded, this one would deal everything, steel plates, mechanical attached, FRP, or external post-tensioning. Because fire can damage anything exposed, right? It doesn't matter it's mechanical or non, it still can lose capacity. So this section applies to everything in there. So let me give you an idea, how do we deal with the fire issue? We know there's a lot of science available out there. There's ACI 216, there's ACE document, PCI document that tell us that concrete, when exposed to high temperature, its capacity will drop with time. And if I look at the compressive stress of concretes, if I take a cylinder and test it at different temperature, as the temperature rises, the compressive strength will reduce. And you can see actually what happened, ductility increased, becomes softer and less brittle, lose capacity. And there are many documents through, again, PCI, ACI 216, and other documents that give you a relationship between the compressive strength of the material and its temperature. It's typically idealized as an envelope. So for example, this is ASCE document. There's a reference in here. It's called Structural Fire Protection. It says that maybe up to approximately 400 or 500 degrees C, which is close to 1,000 degrees Fahrenheit, I can assume the compression capacity is the same, and then it drops after that. And then there's a similar one in the Eurocode. And similar thing for steel. I have a lot of information available in reference. This comes from Eurocode, for example. Stress strain diagram for steel. Linear elastic, plateau. I'm not showing strain hardening in here. As the temperature rises, I can lose a stiffness first, and then strength start dropping. This is close to 1,000 degrees Fahrenheit at 500 C. And then beyond that, it drops significantly. So what does that mean? That means as the temperature rises, the strength of the steel will drop. This is the Eurocode, again, this is ASCE. So it's showing me similar thing, up to maybe 400 or 500 C. Maybe it's okay. Beyond that, the strength will drop significantly of the steel. So that means for me to calculate that capacity we talked about to compare to this 1.2 dead and 0.5 live for fire, I need to know exactly what's the temperature of my reinforcement to figure out what is its capacity after 1 or 2 hours, and then come back and check, which is a little bit different than what we used to do, but it's required for fire rating. Why is it this important? Because when you do new design, we design a proportionate structural element and have adequate steel in it, and we have proper cover, right? Assuming construction is done correctly. So the fire issue is addressed by the cover. Now I'm adding more reinforcement or adding a load on the structure. When you add reinforcement or load, if you change the capacity or the demand, you're actually changing the fire rating, because as you'll see, fire rating is a function of both. It's a balance of capacity and demand. If you increase the demand, you'll drop the fire capacity. Why? Because that means it can fail now earlier than it used to be, as the strength will drop. How do I determine properties? They are the temperature of the reinforcement. There are now many charts available, some of them 216. This is also in your code. Imagine this give you like almost a quadrant of the beam, in which it tells you based on the thickness of the cover, the dimension of the beam, you can figure out the temperature profile. And if I have steel bars, I can determine their temperature. I can also do thermal analysis. There are ways and software, many of them available right now. We use some COMSOL, for example, in which you put standard fire curve. There's a standard STM 119, and it can tell you at any time what is the temperature of your reinforcement. And if I know the temperature of my reinforcement, I can go back to those charts. And I show you one actually from 216. This is the one here we use in the US. That give you the relationship between the temperature of the bar and its capacity. This is the structural steel for structural component. This is mild steel for reinforcement. And this is post-tensioning reinforcement. So if I'm looking at my steel reinforcement and I have a chart and I figure out the temperature of the steel, let's say it's close to 900 degrees, that steel bar will retain approximately 70% of its capacity. Let's say this is after 2 hours I'm trying to do this analysis. 70% of 60 KSI is 42 KSI residual that I can use for analysis to verify in there. Or if you use SI units, let's say it's a 400 MPa approximately, it's give you like 280 or something like that, 280 MPa that you need to use for analysis. So there are ways I can determine the temperature of my reinforcement and their residual capacity to compare with the demand. Now, bits and pieces I put in there. Let's try to connect them all and connect the dot to make sure that we understand it. Imagine you have a simply supported beam. And on that simply supported beam, you have a uniform load applied to it. So what happened is that that uniform load will create bending moment diagram. WL square over 8, this is standard formula to use for design. I'm going to put in its steel reinforcement to give me capacity higher than the maximum bending from external load. It's a standard design approach that we use. And this is, let's say, design criteria per the US ASCE 7 and ACI 318. Now, what's happening during fire? During fire, my material is degrading. My steel strength is getting reduced. And as a result of that, my capacity is going to drop. It's going to be a lower capacity as a result of that. Typically, if I have fire, I assume that the top concrete in compression, it's going to be protected by the thick concrete, is going to be cold. So really, mainly the properties or the capacity during fire event is controlled by tension reinforcement capacity. So now, what 562 tell me is that you calculate this reduced capacity, and you can see here there's no reduction factor, almost 1.0. That is my capacity. I compare it with the demand for fire. And that is the demand. Now it's been reduced from here to here. If I have adequate fire capacity, IR capacity compared to the reduced demand, that means my system has proper capacity, has adequate fire rating in a way. That's the spirit of fire rating. That's the meaning of fire rating, is capacity after a certain time versus the demand. And if that's the case, then I don't have to worry about fireproofing. All this analysis should be done without the contribution of the external system. I'm assuming it's damaged by fire, and this capacity does not include any of the FRP or steel plate or PT. And if it doesn't satisfy this, that means really my system, without the external system, doesn't have adequate capacity. Therefore, what do I need to do? I need to apply fire protection to it. Now I understand, I verified it, I'm adding load or capacity. It's not going to be good, the fire rating, so I have to apply additional fireproofing to it to improve the capacity. I can fireproof the PT system and then use it in calculation if I show that I have adequate protection to it, and that will increase my capacity. Or sometimes I can ignore it. I'm going to apply fire protection to the concrete itself. I'm not going to fireproof the PT. I'm going to put some fireproofing on the concrete itself to increase its fire rating. So the existing reinforcement will give me higher capacity. As an engineer or a designer, you can play with these things and figure out what is the most economical way to do this thing. How we do that? There are many systems for fireproofing. Now there are systems for fireproofing of RP available in the market. There are spray applied material and intumescent coat that we know works very well with steel that we can apply to external steel. And by doing that, I can achieve proper fire rating. I've seen cases in which engineers specify fire rating all the time, just want to be conservative. In other cases, they do through analysis because they want to save the client or the owner the cost of doing this. There's a balance between the two. There's structural demand and there is other requirements. And again, if none of these work, if I find that I have all these issues, I'm trying to increase the capacity beyond 40%, let's say, beyond 50%, which is significant for external, or fire issues become an issue, I can always default to what? The old things that we've been doing for 100 years, which is adding more concrete and steel, right? I can roughen the surface, put some dowels, form the concrete, pump some cementitious material, and increase the capacity. In this case, I added a reinforcement system, and then the cover is what doing? Is providing the fire protection. It's standard thing that we do all the time. And it will also improve the fire rating of the existing reinforcement because my new concrete is much thicker, the concrete cover. Same thing with external PT. I've seen external PT in which we, for example, end up putting it in a duct and centralize it and fill it with the grout to give it some concrete cover protection on it, or embed the entire PT system in concrete. In this case, these beams had strength and serviceability issues, so PT was required and was required during a fire event, so it was encased all in concrete. So the jacket included posttensioning and included mild steel reinforcement. So there are many ways you can do that. Things to keep in mind, just to summarize, is now there are two limits for the strengthening that we try to introduce 562 in the new ACI 562. One to address during non-fire typical operation, one during a fire event. And during typical operation, that limit applies mainly to epoxy bonded system, and that limit really gives me, on average, maximum 40% increase. I use this as a rule of thumb. If somebody tell me, I want to increase the capacity of the slab by 60%, I'd immediately tell them FRP or epoxy bond is not going to work, just based on knowing that limit. That limit is a function of dead load to live load ratio, but this is an average. If they tell me 30%, I say, oh, well, you can use FRP. It probably is going to work very well. So this is ambient. Now, during fire is different. During fire, I'm going to use reduced material properties. I'm going to do fire rating evaluation to see if it's going to work or not with the phi factor of what and actual behavior of the system. And one thing to keep in mind is there's lots of manufacturers out there with all kind of fireproofing material. You cannot just accept the words, so you have to always ask for a test. And there's a challenge in here because, for example, if I have a concrete and I'm sprayed with fireproofing, you may find there is not a lot of data available on that behavior. So you may have to engage someone or do tests, or the manufacturer may get you that data. What's the combination of concrete cover with another 1 inch, for example, spray applied effect on the structure? All these things you have to account for. Okay, so that's in a nutshell, section chapter 5 of the ACI 562.